A study out of the University of Durham recently found that people have an easier time inferring what happened in the past rather than what will happen in the future. It wouldn't have been hard to predict this result, would it? But this is not the study that I want to talk about today. Instead, I've a very thought-provoking prediction that says global civilization is about to dramatically change. This study builds on an idea going back to the ecologist and system analyst Crawford Holling, which he popularized in his book Panarchy. He said that all types of complex systems, including human civilizations, go through a cycle of 4 phases. The first is a phase of exploration in which complexity rapidly increases because resources are abundant, for example, energy. Then there is a phase of conservation in which the system settles on a status quo that can last for a long time. However, the longer the system remains there, the more efficient it becomes at using resources and the less resilient it becomes to disturbances. This quasi-stable phase is then inevitably followed by a breakdown, which is called the release. After that, that's either the end of the system, which means it'll forever remain at low complexity, or it'll manage to reconfigure and start another cycle. The new paper claims that global civilization is currently in the breakdown phase and nearing a reconfiguration. So it's basically party, settle down, midlife crisis, and then either therapy or eternal stagnation. Crawford Holling drew his insights from biological systems such as forests, but argued that the cycle stems from the nature of complexity itself. It's because ultimately, whatever we do, everything from Amazon deliveries to antibiotic resistance is a reorganization of matter, energy, and information. Though Albert would like to point out that matter really is just a type of energy. This complexity cycle has previously been used to explain the rise and fall of earlier civilizations, such as the Roman Empire. The new study now is an attempt to apply this system's thinking to the current state of the world, the industrial phase of human society. The author says that there are multiple lines of evidence that we're currently in the breakdown phase. One line of evidence is the repeated smaller and larger financial crises and the increasingly larger fluctuations in GDP in the recovery phase. Then there are the multiple planetary boundaries for resources that we are depleting, the pollution we are causing, and the mounting evidence for the beginning of a biosystem collapse. Other lines of evidence are the rapid increase in the adoption of electric vehicles and renewable energy and the spread of artificial intelligence that is changing human work in many professions with the robot revolution underway. I'm just waiting for the day AI replaces my job of telling you AIs are replacing jobs. The author argues that we're currently at crossroads. Soon it'll become apparent whether we can reconfigure our organizing system, as he calls it, to one that can deal with the higher complexity we'd need to enter a new cycle. He writes that the success of the emerging new life cycle requires an organizing system premised on highly networked and decentralized models of localized ownership and creation, and that we need to adopt dematerialized post-scarcity worldviews that he calls an emerging post-materialist paradigm. I don't know about you, but I don't want my pension savings to dematerialize, so I'm not so sure about this. I also don't buy the entire decentralization idea because what we see with AI is exactly the opposite. There are but a few companies about to become so powerful they'll make the Roman Empire look like a lemonade stand. But well, I'm just some YouTuber and this study doesn't come from anyone, but from Nafis Ahmed, a British investigative journalist with a PhD in international relations. He's previously correctly predicted numerous other world events, such as the 2008 financial crash and the escalation of the Russia-Ukraine conflict, according to his own website. So maybe not the most reliable source. Let's have a look at this supposed prediction of the 2008 financial crisis. It comes from a 2006 article in which Ahmed wrote, "The source also said that leading US financial analysts privately believe that a collapse of the global banking system is imminent by 2008. The same anonymous source also said that global oil production most likely peaked in 2004. It's now 2024 and global oil production still hasn't peaked. I wouldn't call that a prediction for an economic crisis. That's an uncommented quote from someone who claims to have talked to someone who believes that there might be a crisis coming. And if you write sufficiently many articles of this sort, it'd be surprising if there was not occasionally a correct sentence in them. So, I think the gentleman is slightly overstating his case. Then again, who isn't guilty of self-advertisement? I don't mean to criticize him. No, really. I'm just telling you this as context so you know how seriously to take this prediction. Basically, not too seriously. But I do think it's worth thinking about nevertheless, because what good is a civilization breakdown if we don't properly complain about it? This is the last episode of our science news in 2024. Tomorrow I'll be back with a different shirt paper. Until then, I wish you all a good start into the new year. In 2011, the Nobel Prize in Physics was awarded for the discovery of the accelerating expansion of the universe through observations of distant supernovae that's usually attributed to dark energy. In a paper that just appeared, a group of astrophysicists from the University of Canterbury, New Zealand, questions the Nobel Prize-winning finding. The discovery that our universe is not only expanding, but that the expansion is speeding up has no simple explanation. There is no normal type of energy or matter that can make it happen. It requires a substance with negative pressure, a property that we've never otherwise observed that indeed we have difficulties even interpreting. Physicists have just called whatever is causing this accelerated expansion dark energy. The simplest type of dark energy is one that's constant both in space and in time. It's then called the cosmological constant, usually denoted lambda. It's become one of the key parameters in the standard model of cosmology, the lambda CDM model, where CDM stands for cold dark matter. The authors of the new paper boldly assert that this is just the wrong model for the universe and that the evidence requires a foundational change to cosmological model. They say that if one uses the correct model, we do not need dark energy at all, not even in form of a cosmological constant. Their argument goes like this. Because there is a lot of matter in the universe, in practice we can't do calculations with the exact distribution of stars and galaxies that we observe. There are just too many. Therefore, for lambda CDM, we make a big simplification. We say that if we average over sufficiently large distances, then stars and galaxies have the same distribution everywhere. This idea is called the cosmological principle. It gives rise to the lambda CDM model that requires dark energy. But strictly speaking, this model is, of course, wrong. Galaxies and galaxy clusters are not uniformly distributed. Instead, it has patches with many galaxies in them, such as the one that we find ourselves in, but then there are big voids in between. It's not uniform, but more like an expanding sourdough starter, if you can imagine a sourdough starter that's several billion light years wide and made of galaxies. This is what the authors of the new paper looked at, a universe that has matter-filled regions like our own and voids. And all these regions do their own thing. They push and pull on each other. The authors call it the timescape model, because time runs slightly differently in each of these regions, but I think they should have gone with sourdough, because I'm sure that after you've forgotten everything I told you today, you'll still remember the sourdough. They say that the idea that the universe undergoes an accelerated expansion as a whole is a misinterpretation of what we observe in our vicinity. It's much like that what you observe in your home city may be a poor description for what happens in the world on average. But if we're careful and use the timescape model, we can then reconcile the supernovae observations with a normally expanding universe without the need for dark energy. To reach this conclusion, the group compared how well the lambda CDM model and the timescape model fit to a catalogue of supernovae observations. The authors use a Bayesian analysis, which quantifies the probability of a model to be correct, and find very strong to strong evidence for the timescape model in the low redshift regime that's in our vicinity. This agrees with earlier findings which have built up for some time that draw the cosmological principle which underlies lambda CDM, and with that the discovery of dark energy, into question. For several decades now, astrophysicists have found structures in the universe that are too large to be compatible with the cosmological principle. Since 2003, astrophysicists have known the Great Wall, a collection of galaxies about 1 billion light years away from us that extends over 1.5 billion light years. Then there is the huge quasar group, which spans 4 billion light years, and also the recently discovered Big Ring that spans 1 billion light years. According to lambda CDM, these large structures should not exist. And yet they do. By the way, this video comes with a quiz that will help you remember what we talked about. What are we to make of this? While I'm sympathetic to the idea of the timescape universe and think it might well be correct, I also think it's too early to declare the end of dark energy. For one thing, analyses like the one in the new paper depend a lot on their assumptions and the entirety of data used, and I'd not be surprised if soon another group claims that lambda CDM is superior after all. Another problem I see with the timescape model is that even though the equations which they used in the new paper have the same number of parameters as lambda CDM, the full model is significantly more complicated than lambda CDM. Using the model would require a steep learning curve for astrophysicists, and that makes me suspect that its adoption will be slow. I'm not saying that this is good, I'm just saying it's what I expect, not least because the authors made a similar claim already 7 years ago and no one paid much attention to that either. As they say, all models are wrong, but some are useful, and whatever your misgivings are about dark energy, it certainly has proved to be useful for explaining our observations. And also, you have to admit that it just sounds very cool. Welcome to 2025. Unfortunately, climate change didn't go away. Instead, the situation is worse now than ever before. A year ago, I told you why I'm worried about climate change. It's because I suspect that climate scientists are systematically underestimating how fast it'll get warmer. If that was so, we'd have far less time to get the energy transition done, which, let's be honest, is already going about as smoothly as a toddler trying to assemble IKEA furniture. The reason I began to worry about this is that I have misgivings. Of course I have. I have misgivings about the way that climate scientists have been making their predictions. A few years ago, they threw out the models that predicted the steepest warming trend by finding some argument for why the most alarming predictions can't possibly be true. Of course, they say that this argument is just sound science, but I'm afraid they just want to get rid of bad news as much as everyone else. What do the data say? In the past 2 years, the global average surface temperature has been on the upper limit of the expectations. It's not yet a huge discrepancy with the models. It could be just a natural fluctuation rather than a trend. It could just go away. But climate scientists are increasingly confused about what's going on. This was well illustrated by a show of hands at the meeting of the American Geophysical Union in Washington in December. NASA climate scientist Gavin Schmidt asked how many agree that we have understood the anomalies in 23 and 24 with all of the information that has been presented here and that exists elsewhere. According to Axios, only a smattering went up. Instead, the overwhelming majority backed the position that a sufficient explanation hasn't been offered and more research is needed. There is something to explain and there is still work to do, Schmidt said. There's been a lot of talk about how the decrease in pollution from ship emissions contributed to the warming because such pollution helps to reflect light back into space and keeps Earth cool. However, several independent studies have found that the effect from declining ship emissions isn't large enough to explain what's going on. It's a similar story with other contributing factors that climate scientists looked at. Volcano eruptions and so. They all contribute, but add them all up and it doesn't explain the observations. So what's going on? Just briefly after this conference, a new study partly offered an explanation. This is an analysis from data from NASA and ECMWF. The authors found that the major reason that global temperatures sparked so high in 2023 was that Earth reflected less sunlight than expected. They say that this is because of a substantial decline in low-hanging clouds. They speculate that we might be seeing the first signs of the changes in cloud cover due to rising temperatures. 1 year of data isn't enough to infer a trend, so maybe the changes in the 2023 cloud cover are just coincidence, or maybe there's something wrong with their data, or their data analysis, or with the inherent limitations of our cognitive frameworks for apprehending intersubjective constructs within a socially negotiated reality. But if they're right, this is very bad. This is because the reaction of clouds to an increase of temperature is the major reason why the predictions from climate models disagree so much. Loosely speaking, high-hanging wispy clouds trap heat and speed up warming. Low-hanging fluffy clouds reflect more light and counteract warming. If this new study is right and it's a trend rather than a fluctuation that we see fewer low-hanging clouds, then the changes in cloud cover will accelerate global warming. But since this is exactly what I worried about in my video a year ago, I want to warn you that this video might be less Cassandra and more confirmation bias. So what's next? The coming year has a good chance to break temperature records again. If you remember, Earth has a quasi-periodic oscillation called the El Niño Southern Oscillation ENSO that swings back and forth every few years between one phase that's somewhat warmer on average, that's the El Niño phase, and then a somewhat colder phase, that's La Niña. 2023 was in one of the warm phases. Middle of last year, NOAA predicted the warm phase would transition to the colder one in late fall, but they've continuously updated that prediction and now say that we'll likely remain in an intermediate neutral phase at least throughout the summer of 2025, and if a colder phase will come at all, it'll likely be a short one. This isn't unusual. You can see in this figure that similar things have happened multiple times in the past decades, but it does mean that it's unlikely we'll see a significant cooling this year. The best metaphor for our reaction to climate change I can think of is that we're like people on a sinking sailing boat fighting about who gets to climb up the mast. We're so worried about international competition, about where we are compared to everybody else, we don't notice that the boat is sinking. But that's what's happening. We're pushing climate zones into different regions too fast for most species to adapt, and we're basically begging for a mass extinction. But don't worry, I'll be reporting all through the apocalypse, so don't forget to subscribe. At the end of last year, we saw an amazing surge in the stocks of all quantum computing firms. I must admit that this caught me completely by surprise. I really should have bought some D-Wave stocks. They shot up by like 1000% since the beginning of the year because of nothing really. So what's going on? Have people just totally lost their mind? It's not a possibility that I'd easily dismiss, but maybe there's something else going on. I recently came across an interesting panel discussion among quantum computing experts that I think sheds some light on what's fueling this hype. This discussion took place in November at the Conference on Quantum Techniques and Machine Learning. The following exchange is between Scott Aronson from the University of Texas in Austin and Edward Fari from MIT. Both have done a lot of work on quantum computing, but they have very different ideas about scientific integrity.
You know, I am dealing with people who see all these papers and have taken from them the impression that, well, there must be a quantum advantage for all these tasks that is known, okay, or else why are people writing all these things about it? I mean, we've seen companies, you know, go public on, claims about, these kinds of applications, or, pitch to investors on these claims, and they say, well, look, there's papers about it. And so I think sometimes, it's not enough when writing a paper to not say anything false. Rather, in an environment like this, one has to anticipate and head off, the ways that people are going to misinterpret things.
Well, I don't understand this. I don't feel this burden whatsoever. I don't care.
All right.
I just don't care.
Well,
I find it odd that you feel like this is, something you have to fight for. I mean, I don't care what people say. I don't care what people say after they read my papers. I just care that my papers are correct. That's it. My papers are correct, period.
Well, okay. I mean, I would say if some people don't feel the burden, then that doubles the burden that other people have.
That's quite something. But before I say more about their disagreement, let me tell you how crazy the quantum situation has become. Quantum computing is an existing technology, but it's far away from being practically useful. In principle, quantum computers could make certain calculations much faster, and that could become useful one day in areas such as material design, finance, or logistics. In reality, the best use cases are rapidly being occupied by artificial intelligence, especially in quantum chemistry. And for quantum computers to become practically useful, the number of qubits that they can work with needs to dramatically increase, from currently around 100 to about 1 million, though the details depend on the error rate and the type of problem. Yes, it's nice that Google demonstrated that error correction works as advertised at 100 qubits or so, but they still need to scale that to 1 million. And the question isn't just whether it's possible, but whether it's possible at a reasonable cost. By my personal estimate, commercially useful quantum computers are at least a decade away. And so, quantum computing companies currently make money by renting out cloud access to small quantum chips for research purposes, which most of them do through Amazon's cloud service. In November, Amazon announced that they're starting a quantum embark program that they say will help customers to get into the quantum computing business, which I remind you is a business that doesn't exist. But the stocks of several quantum computing companies, including D-Wave, Rigetti, and IonQ, promptly shot up. The surprise surge even impressed CNBC's Jim Cramer, who correctly noted, however, that these companies don't have any revenue.
So let's start with the unprofitable quantum computing plays, because the best performer of November, at least so far, is a company called Quantum Computing. That's QUBT for you home gamers. It's up an astounding 588%. That's closely followed by two more quantum plays, D-Wave Quantum and IonQ, both of which have more than doubled month to date. That last one sounds like a TV station I'm not working for. Honestly, I have no idea what's behind the sudden interest in these quantum computing stocks. Don't ask me to explain the concept either. You need a physics degree to get your head around it, and trust me when I say that most of the buyers do not have one. Again, I have no edge in quantum computing, but I do know that QUBT is losing money and has hardly any revenue.
Then in December, there was the now infamous Google press release that claimed they'd found evidence for parallel universes, and the stocks of anything quantum rose even further. This time we got Yahoo Finance commenting on the matter, again pointing out that none of these companies are profitable.
The crazy fast capabilities of quantum computing will be indispensable for training AI models, collecting data, and modeling systems. That's according to Google Quantum AI's founder. He hopes it will enable breakthroughs in medicine, batteries, and energy alternatives.
In the quantum computing space, you got IonQ, Quantum Computing, D-Wave Systems, and Rigetti Computing have all seen their combined market caps surge 171%.
Though more broadly, quantum stocks, they've been under a bit of pressure. Currently, none of them operate at a profit. Both D-Wave and Rigetti have faced stock delisting multiple times due to low share performance, and the runway for mainstream adoption of quantum is a long one.
Middle of November, the stocks started to drop again, but still the market is expected to grow, according to some forecasts, by more than a factor of 10 within the next decade. Why? Why is this happening? Well, that returns us to the panel discussion. In it, Scott points out repeatedly that physicists produce a lot of papers on quantum computing. Most of these papers aren't useful because not everything that is somehow quantum is faster than a conventional computer. In fact, most of the time it's not. But physicists frequently fail to disclose this. By doing so, they raise the impression the field is rapidly progressing when the truth is that not much is happening. This is why Scott is saying it's not enough to not say anything false, but that scientists need to make sure that what they say can't easily be misinterpreted. To which Edward Forey replies, "I don't care what people say after they read my papers. I just care that my papers are correct." Now imagine that this exchange wasn't about quantum computing, but about drug development. You write a paper that only contains correct statements about a drug that cures cancer, and somewhere in Appendix D, you mention that your trial was, of course, as usual, done in mice. Most people will miss that, and you know it. But you didn't say anything false, so you don't care. If people misinterpret your finding, you don't care. If companies present your paper to collect money from investors, you don't care. If the company goes public and your neighbor buys stocks and then loses his savings when the bubble bursts, you don't care. I don't think that this attitude will do much to increase trust in scientists. Now look, I don't want to blame an entire research area for what one guy said. But I too have noticed what Scott is saying. A lot of authors who publish on quantum computing are not very forthcoming with details which are necessary to put their work into context. How much does this affect quantum stocks? I guess we'll need a quantum computer to find out. The craziest economic bubble I've seen in the past years, the hydrogen economy, is about to burst. That's really good news. The hydrogen economy is the idea that we'll use hydrogen to store and transport energy from intermittent renewables. It's a good idea in principle, but in practice it makes no financial sense. Investors are now beginning to see this. Plans for green hydrogen production, that's hydrogen produced from renewable energy, have been cancelled all over the place, and pipelines as well. According to the industry analysis group Westwood Insight, about a fifth of the green hydrogen projects in Europe have now been cancelled. But it's not an exclusively European phenomenon. In October, one of the largest energy companies in Australia pulled out of plans for a facility to produce hydrogen from renewables. In November, the American industrial gases company Air Products pulled out of a green hydrogen project in Texas. If a project is too airy for a company called Air Products, that should really tell you something. The Financial Times reports that stocks of some of the biggest hydrogen companies in the US and the EU have been dropping dramatically throughout the year, between 30 and 50%. What's going on? It's reality coming back to bite. Using hydrogen to store energy sounds good at first. Combined with oxygen, hydrogen simply creates water plus energy. Zero pollution, zero guilt, but not zero problems. First, there's the obvious that hydrogen is a gas, and when mixed with air, it's highly explosive. To be useful as energy storage, it needs to be kept. That's technically not all that difficult, but it's inconvenient and can be dangerous. Though this is the least of the problems. A bigger problem is that hydrogen, because it's such a small atom, creeps into pretty much all materials and quickly degrades them. This affects everything from storage tanks to pipes to electronics and makes maintenance costly. Then there's the issue that the fuel cells that create electricity from the hydrogen require rare metals. But the biggest problem is that it's just extremely inefficient. Using energy to create hydrogen and then converting that back into energy has an efficiency somewhere around 40% optimistically. Realistically, it's far lower because hydrogen production as a chemical process becomes less efficient the more often you have to ramp it up and down. This is unfortunate because that's exactly what we'd need to do to store energy from intermittent renewables. Basically, using hydrogen for energy storage is like trying to run a marathon in flip-flops. You'll get somewhere, but that's probably the emergency room. Yet the USA, the UK and the EU have all invested heavily into this. But now the numbers are coming in and they're not looking good. In April, the British accounting firm PricewaterhouseCoopers published a report about the status of green hydrogen projects worldwide. In this figure, you see a comparison of the plans for 2030 in light pink with reality, that's the black dots. The dots are hard to see because they're so small. To give you some numbers, the European target for 2030 is 120 gigawatts in installed capacity. Operational at the moment are 0.2. The International Energy Agency has found pretty much the same thing in a report that came out in the summer. To reach the plans for 2030, we'd have to scale up production of global green hydrogen by a factor 200 or so within 6 years. I say it's the craziest bubble I've seen because I don't understand how this could have happened. Yes, AI is a bubble too, and so is quantum computing, but in these cases, at least I can see why that happened. But hydrogen? One speculation for what happened is that it was a case of green hydrogen lobbyists overturning or circumventing scientific advice. The European Court of Auditors, the EU's fact-checking body, recently had a close look at the EU Commission's plans for a hydrogen economy. It found that the plans are simply unrealistic. They were never achievable. They write that renewable hydrogen targets were driven by political will rather than being based on robust analyses. Another speculation for what happened is that the lobbyism came from the fossil fuel industry. This is plausible because almost all current hydrogen production comes from natural gas. This is the so-called blue hydrogen. If we designed our economy to work with hydrogen, but then the green hydrogen doesn't come by, we'd just be using natural gas in a less energy efficient way. You can see why BP might like the idea. I don't know if either of this is true. I'm not much of a conspiracy theorist, and I tend to think that this wasn't so much lobbyism as what psychologists call motivated reasoning. It sounds like a good idea. People like it. They wanted to believe it. I still haven't figured out how to shorten stocks. I should really look into this. Thanks for watching. See you tomorrow.